Hello everyone. So here we are started. We are starting going to start the first chapter of discussion, that is relations and functions. Firstly, we'll start with what is relations. So in relations, in class 11 we discussed about Cartesian product of sets. Now we extend our ideas to relations in a set. Obviously, here relation in a set. A relation R is in a set A is a subset of A cross A. So what we can say here, a relation in a set A is subset of A cross A. Thus, R is a relation in a set A. Double implies that R is a subset of A cross A. If A comma B belongs to R, if A comma B belongs to R, then we can say this particular part, that is if A comma B belongs to R, then we can say that A is related to B and write A is related to B like this. If A comma B does not belongs to R, then we say that A is not related to B and write A is not related to B in this format. So we just denote the relation like this, yeah, this way. Let A is equal to let A is equal to 1, 2, 3, 4, 5, 6, and R be a relation in A given by R A comma B such that A minus B is equal to 2, then we can obviously write here because A minus B is equal to 2, so we can feed any value here of A, that is 4, 2 is also possible, 3, 1 is possible, 5, 3 is possible, 6, 4 is possible. Clearly 3 R3 is related to 1, 3R1, 4R2, 5R3 and 6R4, but 1R3 is not possible because A can't be 1. It will have negative value, that's clear. So this is the way 3R1, 4R2, 5R3 and 6R4 can be the relations possible here. What is the domain and range of a relation? Let us understand the domain and range of a relation. Now, if let R be a relation in set A, then the set of all coordinates of elements of R is called domain of R, written as DOM of R, and the set of all second coordinates of R is called the range of R. And we write range in bracket R. Domain of R for a set in a roster format A is such that A comma B belongs to R, bracket close, and range of R B such that A comma B belongs to R. So we can say the first coordinate of the elements of R is called a domain and the second coordinate is called a range. For example, we have A is equal to 1, 2, 3, 4, 5 till 16. We are having an R be a relation in A given by A comma B is such that B is equal to A square. Obviously, B is equal to A square can be 4 comma, it can be 2 comma 4, 1 comma 1, 3 comma 9, 4 comma 16. The domain of R is we have 1, 2, 3, 4. That is the domain of R. The first coordinate. The range of R is 1, 4, 9, 16. That is the range of R. So in this example, because this was the defined set, so range of uh, R set was defined like this. So domain of R will be like this, and range of R will be the second coordinate. Some particular type of relations, what we can see can be uh, empty relation or void relation. So some in the case of particular relations, empty relation or void relation, relation R in a set A is called an empty relation. If no element of A is related to any element of A, and we denote such a relation by phi. So empty relation means there is no relation, or there is a void relation, a relation R in a set A is called an empty relation. If no element of A is related to any element of A, and we denote such a relation is called phi. R is equal to phi, a subset of A cross A. A is equal to 1, 2, 3, 4, 5, and let R be a relation in A given by A comma B. A minus B is equal to 6. It is not possible, obviously. Clearly, no element A comma B belongs to R satisfies the property A comma B is equal to 6. So R is an empty relation in A. So we have now seen the empty relation or void relation. R is an empty relation in A. Universal relation. A relation R in a set A is called a universal relation if each element of A is related to every element of A. A comma A cross A is a subset of A cross A is a universal relation on A. Here we have A is equal to 1, or 1, 2, 3. Then the R is A cross A means it will be 1 comma 1, 1 comma 2, 1 comma 3. Similarly, 2 comma 1, 2 comma 2, 2 comma 3, and 3 comma 1, 3 comma 2. So it will be 9 elements will be there in the is the universal relation in A. So this is the concept here. So the important concept is the universal relation in identity relation. The relation I A is equal to A comma A such that A belongs to capital A is called the identity relation. A is, let us say, A is set having elements as 1, 2, 3, then IA is equal to 1 comma 1, 2 comma 2, and 3 comma 3 is the identity relation of on A. So there's also an important part, universal relation we have here in each universal relation. Actually, let us say there are three elements. Obviously, every element will have a relation is there with every single element with each other. That's why it will have for three, it will be nine. It will have 9 elements here. The universal relation in A, and similarly for identity relation, we have same repetition is there, so it will have 3 elements here. This is the identity relation on A. Various types of relations. Let us see. A is be a non-empty set, then a relation R on A is said to be reflexive. If A comma A belongs to R, for A small a belongs to capital A. If A R A for that is, if A R A for each A belongs to A, then it is reflexive in nature, symmetric whenever A comma B belongs to R, B comma A belongs to R. For all A comma B belongs to A. If that is, if A R B is implying B R A for all of this, then it is symmetric in nature. Uh, and whenever transitive, if A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R for all A, B, C belongs to A. That is if A R B and B are C. Then if it is there, A is related to B and B is related to C, then A is related to C. we can say that. So we have three type of relations: reflexive is there, symmetric is there, and transitive is there. Equivalence relation. A relation R in a set A is said to be an equivalence relation if it's reflexive. So it is important to understand that equivalence relation, a relation R in a set is said to be an equivalence relation if it is a reflexive, symmetric, and transitive, all of them together. So we'll come back here after a short, you can say a break, or we can say a pause. We'll come back and continue from this particular